Let me start with a small disclaimer. I'm not a device physicist. I'm not here to tell you how to design a power transistor. But I do spend some time on connecting physics, manufacturing realities, economics, and industry strategies. And occasionally, when those four things lines up, you see something interesting. Now, for some time ago at a conference in Shenzhen, the discussion was mostly about EVs, 10 minutes charging, the usual topics. But what caught my attention wasn't a car. It was a consumer electronics charger, because this charger wasn't based on gallium nitride. It was based on silicon carbide. And that raises a question worth turning into a case study. And that made me think what silicon carbide was supposed to be for. For years, the industry story was very clean. Gallium nitride for consumer electronics, small, fast, high frequency, compact chargers, silicon carbide for EV and industrial power, high voltage, high temperature, and high reliability. In other words, gallium nitride lives in your backpack, silicon carbide lives under the hood. So seeing silicon carbide show up in consumer electronics immediately tells us something has changed. Not just on the technical side, but also on the economic side. The physics, without scaring anyone away. Let us touch physics briefly, just enough to be useful. Silicon carbide belongs to a class called wide bandgap semiconductors. What that really means is, in practice, is two things. First, less energy is wasted as heat when electricity flows. And second, heat escapes more easily once it's generated. If gallium nitride is like a very fast sports car, agile, lightweight, extremely quick, then silicon carbide is more like a heavy-duty engine, just like a tank. It's not trying to be the smallest, it's trying not to fail when things get hot, stressful, or unpredictable. That's why EV loves it. So why consumer electronics suddenly makes sense? So why would the same material show up in consumer electronics? This is the first key insight. Let's have a look at it. A consumer charger does not need automotive grade quality. Lower voltage, lower lifetime requirements, not safety critical. Which means something very important. Not all silicon carbide needs to be EV grade to be economic valuable. So materials that doesn't meet the strictest automotive standard can still be more than good enough for consumer applications. That changes addressable market immediately. Power density is catching up with consumers. Alright, this second insight. Consumer power levels are no longer consumer-like. We're talking about 180 watts, 200 watts, 240 watts USB-C chargers. And now for gaming laptops, these numbers are constantly increasing. At these levels, the problem is no longer the switching speed. The problem becomes heat density. This is where silicon carbide's thermal robustness starts to matter more than the footprint. Not because it's smaller, but because it's stable. And in premium consumer electronics, reliability itself becomes a feature. EV slowdown and manufacturing reality. Now let's zoom out a little. EV adoption hasn't stopped, but it has slowed unevenly and regionally. At the same time, silicon carbide capacity has already been built, capacity has already been deployed, foundries still need volume. Wafers don't follow narrative, they follow utilization. So when the EV demand softens, the industry naturally looks for adjacent markets that use similar devices, tolerate different quality thresholds, provide learnings and cash flow. So I think consumer electronics fits that description better than many people expected. Why 12-inch silicon carbide is the real signal. Now we arrive to the most important of this case study. 12-inch silicon carbide. Nobody does 12-inch silicon carbide epitaxy as a science experiment. Epitaxy at that scale only makes sense for power electronics, wouldn't you agree? So here are 3 things that power electronics only makes sense if you believe volume matters, cost curve matter, yield learning matters. So here's the key point. You don't scale silicon carbide to 12-inch if you expect it only to remain at EV only. Lower tiers application including consumer electronics often how new wafer standards mature? Maybe not at the top, but where good enough is good enough. A reality check on AR/VR narratives. And here is merely a personal opinion about AR/VR and why I'm cautious about the older narrative like 12-inch silicon carbide being driven primarily by these applications. Yes, Meta have invested billions over the last decade, but it also just laid off some of his staff at the Reality Labs. Yes, silicon carbide has interesting optical properties, but AR/VR does not consume wafers at that scale in my opinion. Power electronics does. If silicon carbide is going to justify 12-inch silicon carbide manufacturing, the volume will almost certainly come from power and energy, not optics. But what if I'm wrong? So what does this case study really tell us? Let us connect the dots. EV funds silicon carbide, EV demand is normalizing, 12-inch silicon carbide manufacturing is advancing, consumer electronics is quietly absorbing non-EV grade silicon carbide, power levels in consumer devices keep rising. This doesn't mean that silicon carbide is going to replace gallium nitride. They will coexist while we're moving towards a segmented ecosystem where gallium nitride optimizes size and speed and silicon carbide anchors robustness and thermal headroom. So at the end of the day, when I see silicon carbide chargers, I don't see curiosity, I see a signal. A signal that silicon carbide may enter its next growth phase, not only through cars, but through everyday power. And if you're thinking about materials, manufacturing, partnerships, or capital in that space, this conversation is worth having.